Okay. This is the utilization of the perceptron, but we have two more concepts in here, like this one. Firstly, we should talk about the multilayer perceptron. Okay? Firstly, assume that we have x1 and x2 data in here, like this one, x2 and x1. Okay? And we have two classes, x, and o. Okay? And we know that this is one class and this is another class. Okay? And so, in order to resolve this problem in here, I need to utilize the two perceptron. Because if we have this class, and so we can build the one hyperplane in here and the other hyperplane is located at this one. And so I can condition the whole the terms in order to what the binary conditions, 1 and 0. Okay? Can assign the each data. But what happens if I need to one neuron to classify all these things? For example, I can choose the some neurons to model these things. This is also a line, but the specific formula of this line could be like this one: x1 minus theta 2 square plus divided by theta 1 plus x2 theta 4 square divided by theta 3. Okay? This is the elliptic formulation. Okay? If we have this information, and so we can build the what are conditions. Just like that. F is equal to the what 1 divided by 1 plus exponential minus g dot. Okay? This is creates this line, and so we can condition to 1 and the other terms is 0. Okay? But this is the specific formula. This is called also the Boltzmann machine. We can drive the nonlinear hyperplanes by using these formulations, but it's too difficult to each data, or to find the correct formulation for each data. And so we need to always use the specific hyperplane, the linear hyperplane in here. This is the elliptic hyperplane. Yes, the internal part is the 1, the other part is the 0. We can condition that. Okay? This is the specific formula, like the circle, for example. Okay? But in neural network, we could not reach the total formulation for specific cases, or it's too difficult. And so we always use these terms. For example, we have another representation in here, like this one, x2, x1, and so this x, o, and then we can divide these terms like this one, and so this is the h1, it's the h2, and so this 1, 0, and 1 and 0, and so this is directly related to 1 and 1, this is the 0, 1, and this is the 0, 0. Okay? The fourth plane is undefined because we don't have the fourth plane. Okay? Because this is the easiest way to condition of the whole data. We can draw with the strict line, the linear line. Because if we have the linear formulation, and then we can train it easily. Because if we take the derivative of these terms, and so we get the complex formulation. to train this network. But in the linear form, we can easily obtain the training rules, like the regression model, gradient descent algorithm. Okay? Okay? So, we have this nomination, and then this is the first layer of our algorithm. This is not the multilayer perceptron. But if we add these terms like this one, x1 and x2 in here, and so we have two neurons in here like this one, and so we can add one more layer in here to take the output y. Okay? Because this is the z1 output, z2 output. We have v1, v2 in here like this one. This is the w11 and w22, which is given in here. Okay? And so this each plane can be conditioned by using these terms. But what is the correct representation of these things? In the next case, we will talk about it, like this one. In the first place, this is our general structure for the multilayer perceptron, because the first layer is the hidden layer, this is the output layer, and we get the y output, z1 output, z2 output, x1 and x2. And so, what's the geometric representation of these terms? In this case, we have the x1 and x2. Okay? This is the first thing. And so, this is directly related to this plane. Okay? These terms can be represented by using this notation. Okay? And so, x and o can be given in here. And so, we have two neurons, and two neurons can be drawing like this one, h1 and h2. Okay? And this is the 1, this is the 0, and this is the 1, and this is the 0. Okay? So this h1 and h2 produces the z1 and z2. Okay? Because it's the sigmoid function. But how come we produce this z1 and z2? Because we have right now like this formation. For example, 0 to 1. Okay? And 0 to 1. And so if we are using the one more neuron, and then we can create another plane in here with the axis of the z1 and z2. Is that right? Because if we have two input like here, this is the axis, but the z1 and z2, and this is the another input to the for the output neuron. We can build another plane in here. And so, in this case, this x and x can be encoded in here, z1 and z2. For example, this is the 1 and 1. And so, 1, 1, and then we have the 1x value in here. Is that right? Because the z2 is 1 and z1 is 1, and x should be given in here, right? Okay. And so the other x is the 0 and 0. Okay. The other x is given in here. You get it? Because the 0 and 0. And so z1 is 0 and z2 is 1. And so the O parameters are given in here or distributed in this range. Okay? This is important. And so, what do I need to split this data in here? How many neurons do I need to? Just one. Because if we put this neuron like this one, and so I can condition of this data 0 to 1. And so this is what, for example, H3, but this is the output. Okay? This is called the multilayer perceptron. Because if we have this kind of data in here like this one, and so we cannot split the each region. But if we are using or adding to one more layer, and so this Z2 and Z1, the hidden parameter outputs are transformed into the what? To the plane. And so if I use the one more neuron in here, and so I can split the whole data. This is called the multilayer input. Yes, this is, for example, this is H1, this is H2, this is H3. Okay? Louder, louder.
If we have a huge number of examples, like for example, if we have 1x between the two poles, so we will need more layers to separate it.
Yes. For example,
More layers, more layers to make more hyperparameters, and
yes.
more layers to separate it.
Yes, yes. For example, x1 and x2. And so we have two neurons in here, like this one. And so we have two neuron, and at the end of things, one neuron. Okay? And each connection can be given like this one. And so each output can be represented by the what? The A1, A2, B1, B2, C1, C2, and this is the Y. And so what's the geometric representation of these things? Firstly, we have the what? X1 and X2. And this is the what? A1, A2. And after that, we have B1 and B2. After that, we have the C2 and C1. After that, we don't have it because in this region we have the Y output. Okay? No. It's your decision. But in the geometric representation, we have this kind of structure. Okay? If we have more than one layer, we will call it to what? To deep network. If we want to train the deep networks, we need to what? Deep learning. This is the basic definition of the deep learning. Okay? Because we cannot illustrate the whole data using one layer, which is the standard multilayer perceptron. Or if we had the two another neurons in a serial way in here, and so this is a deep network, because we cannot illustrate the data distribution from the what? From the inputs. So there could be a deep meaning in here, or we cannot see this information. No, it's the layer to layer. Layer adding one layer. And so one layer divides the whole data. But it's not enough. And so we can add another layer, and so we can create the what? The another representation. And so if that's enough, and okay, we should add the one neuron. Okay? This is the deep network. Okay? Any question? So, the structure of neural network should be given at this time, like this one. Structure of NN can be given like this one. Firstly, we need to have some threshold values in here, like this one. We have one hidden neuron, and we have the output neuron in here. Okay? So this is the what? The x0, usually 1. This is the xj. This is the xd. D is the number of the class. Okay? And so each neuron connected to another neuron in here with the coefficients of the what? The w, h, j. Okay? And so in the hidden layer, call it, we have a specific connections like this one, and so this is the other coefficients like VEH. Okay, so if we have this information, and so we have the Z0 plus 1, because this is the another bias value, because each layer should need a what? A bias value in order to what? Condition that. If you are not using the bias, and so whole the data or the whole the lines is passing to the 0, okay? In geometry we cannot draw this line without bias, okay? In geometry, this is the meaning of usage of the what? The bias value, okay? Yes. And so this is the what? This is the restriction to what? Classify all the values. If you don't want to use the bias value, and so you may need to add what? To many neurons, okay? Or many layers. So in the last case, we have the Y1 value in the output, YE value, and YK value. K is the class number in here. H is the hidden layer number, and J is the what? The input number. I is the index of the K. Okay? This is the basic representation. And so, how can we build this structure? By using the what? The math, or mathematical formation. Firstly, ZH is equal to what? This formation. 1 divided by 1 plus exponential, and so there's a summation in here like this one, J to D, okay? VHJ times XJ plus VH0, okay? But in this case, we use the what? The sigmoid function, okay? This ZH can be represented by using this formula in general form, okay? And so YEI is equal to what? Y transpose I times Z, which is equal to the what? H equal 1 to H, because this is the hidden layer in here, and so VEH times ZH plus Z0. Okay, this is the output of these things, and so this is called to the what? X training to Y training. It's called the map. Okay, this is the general representation of the what? Our network. Okay, but there is some problem in here. How can we train this network? How can we train this network? So, this network can be trained using backpropagation rule. Okay? What is the backpropagation? Backpropagation means that we could minimize the error. To what? To propagate all the errors to the back. For example, if we have any error in here in the output, and so this error propagates to in the backward position. To what? To minimize this Y error. But how this is happen if we want to change, or if we can change the whole the parameters W or the V value in here, and so we can change the minimization problem, or we can reduce the error between the training data set to the output. Okay, and so in order to minimize these things, we can propagate the whole the errors in the backward way. To what? To update your coefficients W and y. Okay? It's not like that. In here, I can explain that because I will get there. Okay? I will derive the whole equation in order to run this code. Okay? And so, in order to apply the backpropagation rule, we have firstly the cost function. Okay? Cost function should be minimized to what, y, and w with respect to the x value in here like this one, and so the total cost function, the training set, rt is the target values in here, and yt is the output of the R network. Just like the regression in the previous week. Okay? We should define this. And so we need to minimize it in order to train your network. Okay? And then we should also select the activation function, AF, in here. In the input, we have the linear neuron. Okay? In the hidden layer, the Z layer, which is called the hidden, we have the sigmoid function. In the output layer, we have also linear neuron, which means that we produce to what the sum line. But if we are choosing the output neuron is the the sigmoid one, and so we can classify the any objects in this region. But we may produce the 0 to 1 value at this case. Okay? We can change it, or we can change the input as a sigmoid. Okay? This is your choice, or your network training property based on the rules of your application. Okay? So just remember that in the last week. In hidden layers, our model is not linear, and we use activation function. Yes, but this is not the case in every case. Okay, when you may choose maybe the linear one or the rectified linear unit in here. Okay, in the most case in CNN networks or the autoencoder structure, we may use or we need to use the REL function, rectified linear unit. Okay. Yes, then the ReLU and also the linear function can do that. There's no restriction because it's kind of the sigmoid function, but in a linear form. Okay? It could be a hard linearity. Okay? Otherwise, we could not do the rectified linear unit. Hard nonlinearity means that, by the way, hard nonlinearity directly relates to at each point we have the only single values or the specific values or the separate values from each other. This is called the hard nonlinearity. And so you can use the linear function like this one, but you cannot use the sinus function because, for example, in this case we have the one value, and at this point we also have one value, and so we cannot train this network. This could do broke the mechanisms of the hard nonlinearity. Okay? So just remember that in the previous week we create the update rules for the minimization problem, and so we can write it down, the y is equal to the y times alpha dE divided by dV, and so w can be updated with the nomination of the dE and dW. Okay, this is the basic structure or the basic utilization of the update rules, because if we want to minimize any area coming from the cost function, and so we can utilize the first derivative order in order to update your code or anything else in here. Because in the regression problem or the gradient descent algorithm, we want to use it because we know that if there is a minimum, and then we can find it by using these terms. Okay? So there are two rules in here like this one. Hidden to output should be calculated in here, because hidden to output is given from this one, and this is what the input to hidden. Okay, this is why we need to propagate in a backward way to this error. And how can we do that? We should give as some specific derivative of these terms, like this one. And dv is equal to what? 1 divided by 2, and all the data is coming here, RT minus, and so the hidden layer output is that h equal 1 to h the h times vh plus v0. This is the bias value in here. Okay, and so we need to take the square form in here with the derivation operation like this one, and so this yields to the what? 2 is coming from this term, and so divided by 1 divided by 2 should be added in here, and so in every iteration we have the RT minus YT is in here like this one, and so R training Y training times, and so if we take the derivative of the internal term in here like this one, this is the minus 1, and so minus ZH. And so this is the what? This is the first update rule related to what? These terms. Okay? And also we have what for input to hidden layers. We need to backpropagate, or we need to utilize the chain rule in here, because if we have this nomination in here like this one, dE divided by dW, dW is stored in the input and output between the input and hidden layers in here, and so this can be written like this one, dE divided by dYi times yi dzh times dzh and dw. Okay, this is the chain rule. Each term express the other terms. But if I choose to use this form, and so we can easily calculate the proper update rule. Okay, this is the chain rule. It's the mathematical notation. Okay, and so in the first place we have dye, so 1 divided by RT minus YT square in here like this one, and so the internal term should be written in here like this one, and so minus 1 should be added in here because this 2 is coming from these terms, and so we should need to take the derivative of y, and so y have the minus or negative terms in here, and so this should be multiplied with the minus 1. Okay, this is the simple derivative term. Okay, and so in the second place we have the dzh, this term. Okay, and so this is equal to the what? The yh zh plus y0 is equal to the what? If we take the derivative of these terms, and so we will get only vh, right? And so in the third place we have dw like this one, 1 divided by exponential minus omega or wtx value in here like this one. This is the simple representation of the sigmoid function, and so this is a special solution we have in here like this one, zh minus 1 zh times xg. This coming from the what? The total mathematical formulation. If you take a derivative for a what? The sigmoid function, we will have this nomination. Okay? Yes. Multiplying. Yes. Exponential derivative. Okay? So this 2 rule must be multiplied in the one domain, and so this term is putting into the what? Into this one, and the other term is putting into this one. Okay, this is the backpropagation rule. Okay? If you have these conditions, and so you can train any network in your application. Okay? So, yeter ki sen iste. Bunu direkt çıkarttırırım size, merak etmeyin. In your exams, I will give some specific question, but the intellectual question or the catch question. Okay? We have some basic questions related to some basic concepts. If you know the answer, you can answer that. But in your no, there is no mathematical formulation in your exams. Okay? But maybe I can show that if you have the 2 class, and so how many neurons can be used your structure, maybe, or how many layers should be added for the imitation of the sinus signal. Okay, this is a catch question. So if you have the answer of these things, and so you have completed the whole task. Okay. Louder, please. I don't understand what you are saying.
Equals to number of weights is a part. Parameters is weights. Parameters is weights.
Yes, parameters is weights. So we should continue with our example in Python. Okay. We need to code the bare metal code in here, like this one. Okay. And so week 3, we should open the Visual Studio Code in here, like this one. Okay? So, yes. Huh? No. Yes, I will share all the videos on the YouTubes, but there's no mandatory rule to be in here. Okay? Week 3 application .py. Okay? And so, firstly, we need to build some examples, but we need to add some specific import operation in here, like this one, the numpy smp, and so import matplotlib dot pyplot to visualize the whole plot operation in here. And so we need to also add the pandas spd, because we need to write the whole data to the Excel file. Okay? Or coming from the Excel file. Okay? So for the general network, we need to create the generate random data in here with some specific noises. For example, mp random seed value in here, like this one, 0. Okay? And so num sample, which is the training number, is equal to 100, and so which means that we have the 100 training data. Do what? For a specific x and for a specific y value. Okay? And so the x1 mp landscape can be used in here 0 to 1, and num samples should be given in here x2 and x3. Okay? And so what's the dimension of our neural network in here? 3. Okay? And so we need to create, to split the whole data to what? To plane. Because if we have a 3 dimension, and so we need to create a plane to what? Split all the data. Okay? So x3, huh? 0 to 10. Range. Yes. Random value system. And so x1 is the what? The 0 to 10 values. And the 0 to 5, 0 to 3. Okay? This is the simple case. Just for an example. Noise can be added with the random normal distribution in here, like this one, 0 to 2, 0 the mean values, 2 the standard deviation, and we should add the num samples in here. Okay? So, in order to speed up your project or your training, we need to normalize all the data. Because if we have the 0 to 1 values, and so in the multiplication form, this value is always smaller and smaller. Okay? And so this speed up your program. And so x1 is equal to what? The x1, the MP mean values in here, the x1, and MP STD x1. You can use this formulation in here, like this one. This formulation to normalize your data. Remember that you can build your data into the what, the 0 to 1, but this is the efficient way of the normalization of your data. Yes, yes, I recommend that because this most useful data representation. Yeah, no, I don't know the z-scores, but this is the most efficient way. Okay, I think. But there are many methods to analyze your data, okay? And you should choose that. What's the efficient way? And in most cases, I don't know which combination is efficient, but on the internet, I can update my knowledge, okay? Because it's unuseful or unnecessary data to be kept in your mind. So, define the neural network architecture, which means that the input size should be equal to the what? 3. Input size, or the input size is the feature number, okay? The 100 is the what? Training number, okay? If we have the 3 different kind of input, and so we need to select this 3, okay? And so we should also give the hidden size. For example, 5. We can change it like the 10, 100. But the output size should be equal to the 1, because so we can generate the 1 values at the output, okay? Because if we want to create these terms in here like this one, and so this y can be generated in here, 7 times x1 plus 12 times x2 plus 5 times x3 plus noise, okay? This is the basic representation of the what? Our output. And so we want to model it. This is the random function, arbitrary function, okay? I can just take the different values in here, for example 8 and 9. This is just a simple example, okay? So if we have this information, and so we should also define the neural network coefficients, okay? For example, MP random seed must be changed in here for a different coefficients from this data. Weights, hidden, input to hidden coefficients, which means that this is the what? W. Okay. MP rand function can be called in here with the parameters of the what? The input size and the hidden size. Okay. This is the matrix. Okay. And so we should add the biases hidden values in here like this one, MP zeros. This is just a vector in here like this one, 1 and hidden size. Okay? This is a vector. 1 and column values. Okay? Yes. So we have also weights to what? The hidden to output, and so MP rand, and so which parameters? Yes. And output size. Right? And so this must be equal to the what? Biases output is equal to the what? Output size. Okay? Biases output. So these are the basic coefficients. Okay? And so we need to give the what to any other parameters, hyperparameters. Hyperparameters means that the learning rate, okay? Learning rate 0.00001. This is the arbitrary number, but it must be smaller number, because each iteration we will add the smallest iteration should be given into what? Into the cost function, okay? And we should give also maxed epoch value 1000, for example. Yes, no, but this is the adaptive learning rate function. Okay, it's the decay function also. So we can use the adaptive and the momentum terms in order to speed up your progress. Okay, but in this case, we will use the constant value because this is a simple example. Because this is the first time you need to learn the neural network. Okay, there is no fantasy in here. Just example to be learned. This term means that if we have any data in here, and so we should create some error body in here, like this one. RT minus YT creates the error values. Okay, and so at each point, 100 points, we can calculate this error values, and after that we can collect the whole error values one term. Okay, in a simplest way, and then after that we will update the what, the W and Y values, and after that another epoch is running. Okay, and just in here I can give the correct representation. Okay, take the question. It's for storing the what, MSE, mean square error, and epoch values. For example, MSE values is defined the least, and the epoch values is defined the empty list. Okay, so for epoch in range max epoch, and so this is what, this is our basic term to what, to train your network. 1000 times we define or we try to learn the patterns of these terms. Okay, so in the first place we should give the forward pass, because we need to apply or we need to calculate the output of the what, our neural network. For example, if we have the input layer in here like this one, the MP array can be given by the what, these terms. Okay, and so also given this term like this one, x1i. Okay, and so okay, it's the right term in here, because the MSC should be given in here the 0, because the initialize the whole error values at each iteration, and after that we need to give the I in range of num samples. Okay, so this epoch is the what, the whole the error values is collected in this for loop. Okay, but this epoch to what, to update your coefficients, because the every data should be analyzed and collected in the one term by using this for loop, and after that we will update the whole the coefficients with the what, with the one epoch. Okay, this is called the batch size. For the what, this the batch size of these things, what, the num samples. If I choose the 30 or 20, and so in each 20 iteration I update the whole the coefficients. Okay, Just take it. Take your question. Okay. And so for the forward pass, we need to give the input layer in here, like this one, the MP array, and so we should give the some structure in here, like this one, x1i, x2i, and x3i. Okay. And so the input layer is assigned to the what? This one, because it's a linear layer. We transfer all the data in an identical way. Okay. And after that, hidden output can be calculated by the MP dot operator in here, like this one. The input layer multiply with the what? The weights input to hidden layer plus biases hidden layer. Okay? And output layer for the in the hidden output, for example, should call the hidden input, and the hidden output or the z values should be assigned to the what? 1 divided by 1 plus MP x value in here, like this one, the minus hidden input, because this is the what? The omega transform dot x. Okay. In here, in the previous example, so we have the 1 divided by 1 plus exponential open and close parentheses, the yes, but this is the hyperplane, this is the sigmoid function. Okay. So in the final output, we should give the final input in here, like this one, MP dot operator in here, and so the hidden output. Okay. And so we need to multiply with the what? The weights hidden to output and biases output. Okay. And the final output should be equal to the what? Final input, because it's a linear neuron. Which it's a linear neuron. Okay. And so the final input should be equal to the final output. Okay. And so at each iteration should be calculated what? The mean square error. How can we do that? Error is equal to the what? Yi minus final output, because the final output coming from the what? Our network, and so Yi is the what? The training data set, which is defined in the above code, right? And so MSC is equal to the what? MSC, or the error times square. Okay, because this is equal to the what? The error square. Okay, and each iteration the MSC is collected. Okay. So what about the back propagation? From these terms, the output is equal to what? Minus 2 times error. Okay. From the what? From the update rules, which is written in the what? In our PDF or the PowerPoint file. Okay. This is the standard definition of this output, and so the hidden can be assigned to what? The output dot with the what? Weights hidden output T times hidden output times 1 hidden output. Okay. This is the exact match for the what? For this term. Just remember that. Okay. Okay. This is the what? The weight hub. This is the hidden. Just this one. this W. The other term is the what? The other term. Okay? And so it's the D hidden, and update the coefficients like this one, and so the weights hidden output is minus equal to the what? The learning rate times hidden output T dot D output. Okay? Because the hidden output should be given in here like this one. This is the basic representation of this code. It's complex, but if you want to analyze this code, this is the exact representation of these things. Because in the Python we should give the some specific dot operator and dot region, and so it may be confusing, but it's not in reality. Okay? And so if we have this term in here like this one, the biases output should be updated with what? The learning rate times the output. Okay? And so the weights input to hidden is equal to the minus equal to what? The learning rate times input layer T dot D hidden. Okay? And so we should also update the biases hidden. Minus equal to learning rate times D hidden. Okay? These are the basic rules to what? To update the whole the coefficients in a bare metal code. Okay? So after that we need to update in the epoch session. MSE is equal to num samples like this one, because at each iteration we add the MSE values in here like this one. Okay? And so after this batch layer is done, and then we will need to what? Move into the other epoch terms in here. Okay? And so MSE values append MSE, this list is created in here, and epoch values append and epoch should be added in here. Okay? And so if the epoch percentage 100 is equal to 0, and then printf the what? The f epoch value epoch. Okay? And MSE is equal to the what? The MSE, to warn the user. Okay? This is the standard definition of the what? The training algorithm for the neural network using the backpropagation rules. Okay? And so how can we predict these values in here like this one? For example, x1, x2 and x3 should be given in here, and so the input data should be given as the what? The MP array format like this one, a double list value x1, x2 and x3. Okay? This is the simple structure for creating a matrix in here. And so hidden input should be assigned to the what? The MP dot in here, the input data times what? Weights input hidden. Right? Plus biases hidden. Okay? And hidden output should be equal to 1 divided by 1 plus NP exponential minus what? Hidden input. Okay. And after that the final input should be equal to the what? MP dot what? Hidden input or output and weights of hidden to output plus biases output, right? And so the final output is equal to the what? The final input. Okay? And so return to the what? The final output 0 and 0. Because it's a two-dimensional data. Okay? And so we need to return to the what? The 0 and 0 value. Okay? In each case, we call the predict function to predict any data. Okay. This is the two-dimensional matrix. And so in each data, x1 is a one-dimensional data, x2 and x3. But in the MP array, in order to build the dot operator in here, matrix multiplication, we should define as a matrix, even if as the one parameter is included. For example, if you have the one scalar values in here, this defined in the what? 1 times y. This y we need to return to 0 and 0 values. Okay? Okay. So in order to visualize the data in here, like this one, the what dot figure should be given in here, plot y, the color is assigned to blue values in here, and the label should be equal to the what? The real target, right? Because the y is the basic training data. Okay, and so line style is equal to the what? The dashed. Okay, so the predicted values can be given with the what? The predict x1, x2 and x3 for x1, x2 and x3 in zip x1, x2 and x3. This is a standard idiom for the what? For utilization of the x1, x2 and x3 in a simple for loop. Okay, this is the idiom of the Python. And so we can search the whole data and assign the whole data into the what? The predict, and then we can create the list values. Okay, standard syntax rule in here. Okay, so we can plot the plot predicted values, and so the color is red. Okay, and label is equal to the what? The neural network prediction. Yes, prediction. So plot x label x sample and plot y label is the what? Value, and plot legend should be given in here, and plot show should be given in here. Okay, after that we can write the whole data into the Excel file, but in this case we don't need that. And so if I run this code, and so in the first place we train the network, and so if I run this code, and then we will have epoch like this one, and so the error goes down like here. And so in this case we have the prediction in the red line, but it's not sufficient. Okay, so how can we change these things? Maybe we can increase the epoch times in here. Okay, so it's more correct, but that's not sufficient for us. Okay, and so if I change the learning rate like this one, for example, oh, This is the most correct values of the what are representation. And so if I change these things 3000 and then the epochs is running on the place. This is the bare metal code for the what our algorithm and our rules. But in Keras, especially for the TensorFlow, we will have some specific functions to build this model. Okay? Or we can change the hidden size parameter. Right? For example, if we assign to two values, for example. And so, if we have these two neurons in the hidden layer structure, and then we will have some less performance in here, because we don't have the sufficient neuron to model all of these things. But if I increase to 10 values in here, like this one, this could be increase my performance to train these networks. Okay?
I think it will drive it
Louder.
I think it would be, we have overfitting here because
Maybe overfitting. But in the validation or the other performance, we should validate the R algorithm, especially for the cross-validation programs. But in this case, the neuron increment in the neuron affects a good way to training the process. Okay? Is there any question? If there is no question,